Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 12, IP version 6, NAT, and Cisco's 3-layer networking model. And if that sounds like a lot of material for one video, it is, but you'll see that IP version 6 here is going to be strong on theory, and that includes becoming familiar with the address formats and zero and leading zero compression. It's my experience at this point that most CCNP candidates really haven't seen much IP version 6 yet, if any. If you haven't, that's fine. This is really a primer and then introductory material, and that's about as far as IPv6 goes on the BSCI exam. But we always want to give you a little extra for the workplace, so I will talk about IP version 6 a bit more at the end of this video. Then we're going to talk about NAT, and if you recently got your CCNA, you have a big leg up here if you are fresh with your NAT theory. We're going to talk about the theory of it for a few minutes, static, dynamic, and PAT, all of which you should know. We're going to introduce a few new terms though, so don't skip over that part of the video. And then we're going to talk about Cisco's 3-layer model, and the same goes for that. You should be very familiar with that from your CCNA study. It's very simple stuff, but I do have some additional information for you as far as that model goes with the BSCI exam. So let's get started with IP version 6. And before we really start with the whiteboards here, just stepping away from that, those of you who have been in IT for a while and may have been on the Cisco certification track for a while, there was a big push a while back, several years ago, to IP version 6. Mainly because we were running out of IP version 4 routable addresses. And it's amazing what we can come up with in IT when we have to. You know, Y2K was going to be the end of the civilized world, and we handled that pretty well. And then when the IPv4 addresses started running out, we came up with a little something called Network Address Translation, or NAT, and tying those in with private IP addresses, we were really able to circumvent the shortage of addresses that was occurring at that time. But there are other reasons that IP version 6 is becoming more popular, and Cisco right now is in the middle of their second big push to get their certified candidates and certified engineers to know IP version 6. Now the first time, frankly, it didn't go over because we all said, we don't need it, we've got NAT. We'll never need IP version 6, so Cisco kind of backed off in their certification programs about IPv6. But now for the BSCI exam, you've got to have the basics down, and with good reason, because this is the second push, but IP version 6 is here to stay now. The widespread usage is starting to hit. I'm not saying that's going to be in your network tomorrow, but it could be there right now. And it is to the point where it's showing up on the BSCI exam as far as the basics go. Anyone who takes the CCIE written or lab exams right now, I can tell you firsthand, you better know IP version 6. And there are a couple of reasons for this. One is that Cisco feels that network security is tighter with IPv6, and with good reason, because there really are no middlemen anymore, such as DHCP and NAT, between two endpoints. And this is possible because IP version 6 uses 128-bit addresses in comparison to IP version 4's 32-bit addresses. And if you're thinking, well, I can guess what you're thinking right now. Oh my gosh, 128-bit address. It's not that bad. But I'm not going to lie to you, that was my first reaction. It's like, it's how long? Because I found that most people seem to think that if they thought this was going to be, if this is an IP version 4 address, then this is a version 6 address, like there were just going to be 2 extra octets on the end of it. I can tell you point blank that is not the case. But they are nowhere near as complicated to work with as they tend to look at first sight. IP version 6 has some other important uses. Mobile IP. This allows end systems such as global positioning systems, GPSs, and IP phones to move without losing connectivity. And mobile IP takes a bit of configuration when you're working with IPv4, but it's built into IPv6. And more devices are going to demand an IP address of some kind. And I'm telling you, one day, and it's not that far off in the future, your refrigerator is going to have some kind of IPv6 address. It's unbelievable how technology is advancing, and just having the IPv4 addresses is not going to get the job done. You could be using it right now and not know it. There could be an IPv6 address on a device in your car. Now, with IPsec or IP security, you may be familiar with that, may not be. It's not an exam topic, but you've probably heard of IPsec. IPsec is compatible with IP version 6, but it takes quite a bit of configuration, but it's built in to IP version 6. And we're going to take an introductory look at IPv6 from this point on, and then, like I said, we're going to talk about NAT and the Cisco 3-layer model. But I want to urge you here, and I will do it again near the end of the video, to do more outside reading about IP version 6 than you're going to see in this video. Because it's coming. It's here, really. And we can't, as network engineers, stick our head in the sand and say, well, you know, I'm never going to have to work with that. I'm going to use IP version 4 for the rest of my life. We don't work with anything for the rest of our lives in this field. We've always got to be learning. And if you learn IPv6 now, you've got a huge head start on people who are just going to ignore it until they have to learn it, and maybe not even that. You can put this term in your favorite search engine. There are some wonderful free websites out there that have plenty of good information about IPv6. So there are some good books out there too, but frankly, there are a lot of free resources on the web that you could use for it as well. So a word to the wise there about learning this stuff. So now that we've said that, let's get to learning this stuff. Enabling it is very simple. One command, IPv6 unicast routing. And some iOSs out there right now won't support it, some will. You can certainly dig into Cisco.com Universe CD, which is a website I've mentioned several times during the course. As a CCNP and possible IE candidate, you need to be fluent with that site. So that's how we enable it, but let's start looking into the nuts and bolts of it. Good exam material here. You're familiar with the IP version 4 header fields. You know, you've seen those, and then of course we had the IP headers you had to know, the TCP headers you had to know, the UDP headers. But things have changed, and you need to know the changes. There are 8 header fields in IP version 6. We've got version, traffic class, which was our TOS field, the type of service field, flow label, payload length, next header, which was protocol type in IPv4, hop limit, which in IPv4 was time to live, TTL, and we still, of course, have the source address and destination address. You need to know those, and there are 5 fields that have been removed: header length, identification, flags, fragment offset, and header checksum. Good stuff to know. We were just talking about that address format. Let's take a look at this. Holy cow, look at that. Look at that IP version 6 address. How are we ever going to work with that? We're going to work with it pretty well. We've got an IP version 4 address, typical address, 129.14.12.200, and then a typical IPv6 address. And as you can see, it's just a little bit longer. We're not exactly just tacking 2 more octets onto an IPv4 address. Now, I haven't met too many networkers who really like typing, particularly numbers. But you'll be happy to know that there are some rules that are really going to shorten these addresses, and you better be fluent with these rules for your exam. And you better be fluent with them when you try to work with this stuff in the real world. Because if you see 2 colons right next to each other in an IP version 6 address, you got to know what that means. If, say, on the exam you see that twice, you better know what that means too. So let's talk about that. There's a little bit of hex conversion in here. Boy, remember way back when you took your intro exam? You had to learn hex conversions. I'm sure you're still fluent with those. If not, you need to review them because you are going to be doing a little hex conversion when you are converting some IPv6 addresses to IPv4 addresses. Believe it or not, there's actually some rhyme and reason, and these are not equivalent. These are just random, but you'll see how to convert an IP version 6 address into an IP version 4 address shortly. But let's take a look at the zeros that you're going to run into in IP version 6 addresses. And we have 2 different kinds of compression. And we're compressing the way that we enter this. We're compressing the way that we express an IPv6 address. Consecutive fields of zeros can be expressed with two consecutive colons. But you can only do this once in a single IPv6 address. I repeat, you can only do this once in a single IPv6 address. Good exam detail to look out for. Because here we've got the original address that I came up with. And using zero compression, you can see right in the middle where I used two colons in a row. And those two colons are used to represent all of these zeros. So that's cutting down on the typing right there, but beyond cutting down on typing, you better know what those two colons represent. And if you are ever presented with a list in a practice exam or a real exam where you see this twice, that's an illegal address. You can't do that. You can only have it one time. So that's zero compression. We've also got leading zero compression. Now, leading zeros in any field can be dropped. But every block that you do this with has to have at least one number remaining. That is, if the block is all zeros, you have to leave one. Now, this is leading zero compression, and you can do that as often as you want. We're going to do this one live. So we've got this particular address we've been presented with, and we're going to use only leading zero compression in this one. So by doing that, let's bring up we have 1, 2, 3, 4 colon, and then the rest of it will look like this. The trick there, I mean, most of that's pretty obvious, but the trick there is watching that final value, the 0, 1, 2, 3. Because with leading zero compression, I was able to get rid of that 0. I can drop the leading zeros, and I have some numbers remaining. So there's no problem with that. The other ones, the other 3 blocks that I compressed with leading zeros, they are, of course, we left one number in each one because that's the rule. I could have used zero compression in here, but I chose not to. I want you to see each concept individually, and then we're going to look at an example of using them both. So let's revisit that, because at first it's a little confusing. Zero compression, consecutive fields of zeros can be expressed with 2 colons, but you can only do that once in an IPv6 address. So what we did with this one, we have 16 zeros right in the middle. We have 4 consecutive fields. We are going to represent those with 2 colons, and the rest of it is the same. That is zero compression. Leading zero compression is when you drop leading zeros in any field, and they can be dropped, and we can do that as many times as we want to in an IPv6 address, but every block we do that has to have one number remaining. So if you've got 4 zeros in a block, you can really only drop the first 3. Okay, so you just have to be careful and take your time with it. We can combine them, and often do. And again, it bears repeating for the 3rd time, I think, that zero compression, we can only do that once, so you kind of pick your spot with that. So if we were going to compress this as tightly as we could, we'd have 1, 1, 1, 1 for the first block. We'd use 2 colons to represent those 2 consecutive blocks of zeros. 1, 2, 3, 4. Now we can use leading zero compression on the remaining 4 blocks. 1, 1, 2, 2, 3, 3, 0. Because I can't drop all the zeros in that final block. I've got to have 1. That's the kind of thing you have to get used to. You have to be able to look at an IPv6 address and say, okay, using zero and leading zero compression, how could I do this? And there's more than one valid way of doing it. Let's look at this. If we only used leading zero compression, it would look like this. That's using leading zero compression only. So those 2 addresses are the same thing. And like I said, if this is your first exposure to it, it's a little confusing. Don't worry about it. Watch this part of the video a couple of times. And again, this is one of those situations where you can make up your own questions. Just write out an IPv6 address and say, okay, using leading zero compression and zero compression, how can I express this address differently? We've got two kinds of local addresses with IP version 6. Because in IPv4, we've got unicasts. Those are going to one host. We've got multicasts. Those are going to a group of hosts. And we've got broadcasts, and they represent all hosts. It's not quite that simple with IPv6, but it is more efficient. Because there are actually different kinds of unicast addresses, each having their own separate function, and they actually allow IP version 6 to route data more quickly than IP version 4 while being easier on the router. There are two kinds of local addresses we need to know about: link local and site local. We're going to talk about site local first. Now, site local addresses allow devices in the same organization or site to exchange data. These are the equivalent to IP version 4's private address classes, which I know you know, and because they can't be used to reach internet hosts. So site local addresses are just like IPv4 RFC 1918 private addresses. Link local addresses actually have a smaller scope than that. They are just that. They are local to the physical link. Now, these particular addresses are not used to forward data. One use for these is neighbor discovery. And what you need to know about that right now is its IP version 6 answer to ARP. Again, I urge you to do some outside reading on this. It'll be beneficial to you for the real world, especially in the future. But neighbor discovery is one use for a link local address. And we haven't looked at all of these address types yet, but I want you should be very familiar with these for your exam as well. These are the initial bits of IP version 6 address types. 001 refers to a global address. Any address that has its first 96 bits set to 0 is an IP version 4 compatible address. Now let's see, we said that an IP version 6 address is 128 bits. And if the first 96 bits are set to 0, how many bits does that leave? 32? That sound familiar? Yeah, that's a good way to remember the number. We know that an IP version 6 compatible address is 32 bits. We know that a IP version 6 address is 128 bits. So for them to be compatible, the first 96 bits have to be set to 0. And we will see how to convert the rest of that address over in just a moment. Multicast addresses begin with all ones, 8 ones in a row. Site local addresses begin with 7 ones, a 0, and then 2 ones. Link local, 7 ones, a 0, and then 1 0. So it's kind of like the first octet rule. You know, you remember class A is this, class B is this, class C is this. Same thing here for multicast, site local, and link local. First 96 bits set to 0, it's an IP version compatible address. And we have some reserved classes here as well. And of course, you know that you're very familiar with the IP version 6 address classes as a future CCNP. And you know they're not exactly contiguous, right? Class A, Class B, Class C, their reserved addresses are not contiguous. But in version 6, the developers took a much more structured approach to IPv6 reserved addresses. Any address that begins with 8 zeros is a reserved IP version 6 address. It's that simple. One of these is the IP version 6 loopback address, which I have put for you there, and that is exactly what it looks like. And you can already see that using leading zero compression, and zero compression is going to make that a lot shorter. How would we do that? How would we express that address using leading zero compression only? Talked about that just a few minutes ago. Let's look at leading zero again. Let's revisit that. We can drop the leading zeros in any field, but every block I do that with must have at least one number remaining, but I can do it as often as I want to. So, using leading zero compression only, it would look like this. Hopefully with a colon. It would look just like that. Because I took the 7 fields that were all zeros and I performed leading zero compression, so that means I had to leave one, and then I was even able to drop the leading 3 zeros off the last block. Now what if I combined leading zero and zero compression? We're going to change this a bit. What if we combine leading zero and zero compression? Well, I changed this. Go ahead and see what you'd come up with for that. Combining leading zero and zero compression. What would we have? Put it over here away from that colon. That's it. Because we use leading zero compression and zero compression, we're using 2 colons to represent all these fields of zeros, and then we just drop those 3 off the last block. So colon, colon 1 actually represents that huge loopback. It's really not that hard once you get used to it. You just have to get used to it. The only way to get used to it is to practice it a bit. But again, you could take 10 to 15 minutes on a lunch break every day and just write out some mock IPv6 addresses and say, okay, how would I do this? How would I perform leading zero compression? How would I perform just zero compression? How would I do this with both? It takes practice. Hey, we talked about those compatible addresses, and again, an IPv6 version 4 address is going to have 96 zeros for its first 96 bits. So that leaves us with 32 bits. So we've got an IPv4 address in there somewhere. And looking at that IPv6 address, the one leading with 2 colons, that's zero compression in action. We compressed all those leading zeros with 2 colons. So now what we've got to do is convert the lower 32 bytes into decimal. And you see how we came up with that on the board. If you're a little rusty with hex conversions, you might want to practice that. You might want to review your hex conversion values. A equals 10, B equals 11, C equals 12, D is 13, E is 14, F is 15. That's it. I just did it for you. But just remember that we're working with fields of 1 and 16 here, not 1 and 10. So when we have D1, we have D units of 16, which is 14 times 16, 13 times 16, and then 1 of 1, which is 1. So that gives us a total of 208. So this is, you can see it's really simple again when you know how and you've had some practice. So all you do is convert the bits just like you're shown here from hexadecimal to decimal, and then you've got your 4 octets. That's it. So you should be able to quickly look at an IPv6 address and first off tell Cisco, yes, this is an IPv4 compatible address, or no, this is not. And then if you're asked to do it, you should be able to. But it's just hex conversion. That's all it is. Let's take a look at some other address ranges, and this one is multicast. You know what a multicast is? You know that IPv4 multicast addresses are Class D addresses with a first octet value of 224 to 239, and that the IPv6 address range, though, for multicast is much larger, but it's just as easy to remember. Any address that begins with 8 ones, or FF if it's expressed in hex, is an IPv6 multicast address. A couple of terms here I want to introduce you to. You will not be performing any route summarization or aggregation with IPv6 addresses on the BSCI exam. But you should know one term that's used with aggregation, and that is site level aggregator. This is a rough equivalent to an IPv6 subnet, except that there will be a lot more routes in an SLA than there will be in an IPv4 summary route. And again, summarization is way, as far as the IP version 6 is concerned, is way out of the scope of the BSCI exam. But I would know about that term. I think that's a good idea. Also, we've got something called an anycast. And this is a brand new animal as far as we're concerned, an anycast. An anycast is delivered to the nearest interface identified with the address, and it's basically defined as a communication between a single sender and multiple recipients. That's what an anycast is. It will ring truer to you as you progress in your studies. So how do we subnet these addresses anyway? Very carefully. But seriously, subnetting IP version 6, again, it's way out of the scope of the exam. But like with anything else we've looked at, when you first look at an IP version 6 address, you think, oh my gosh, how am I ever going to learn to work with these addresses? Then you watch this video, do a little practice, and you go, well, okay, it's not that bad. And it's really not. But subnetting and summarizing IPv6 way out of the summary of the BSCI. You do need to know that the site level aggregator in IPv6 is going to handle subnetting, and you'll be able to create quite a few subnets because that field is 16 bits long, which allows us to create over 65,000 subnets. Something we can go into a little more detail with, and that we will go into some more detail with, is auto configuration. IPv4 has DHCP and IPv6 has auto configuration. It's the next step in a device acquiring an address when it boots up instead of giving it a static one that's basically lost when it's not on the network. Now, DHCP, it's still required for the host to come up, it boots up, it gets on the network, and it sends out a request looking for a DHCP server. It's got to ask a DHCP server, what's my IP address, what's my mask, how long do I have it, what's the lease, all that stuff. You know all that stuff. But here, auto configuration allows a device to get its IPv6 address without having to ask for it. But the host does need some information from an IPv6 router. Let's take a look at how this actually works. What's going to happen is here with host A, and we'll say that's the one on the top there on the left-hand side, host A is going to assign itself a link local address. And then it's going to test it out. It's going to test the link to make sure that no other host is already using that particular address. So while IP version 4 is polite, this host would come up and say, hi, DHCP server, can I have an address? This now with IP version 6, it's got an attitude. It's like, hey, I'm taking this address, and I hope nobody else is using it. But if someone else is using it, then we're going to have a little bit of a fight. Now, this message is called a neighbor solicitation message that you're seeing right now. It's sending a message out on the link saying, is anyone else using the link level address I just gave myself? Neighbor solicitation. Now, what could happen is that one of the other hosts on the subnet, on the physical link, could say, hey, I'm already using that link local address. This is called a neighbor advertisement message, an NA. Now, if host A doesn't hear something like that, then it goes forward with the auto configuration process. And host A will then contact the local router that we see there at the end of the segment, and it's going to contact it for information on what to do next. And that communication can take place in one of two ways. And let me bring that whiteboard back up. I have put this here for you. And the top three paragraphs we've already gone over. But when host A contacts the local router on what to do now, one of two things is going to happen. Now, host A is either going to send a router solicitation message, an RS, to request information, or it's just going to wait passively for a router advertisement message, an RA. Very important acronyms. I know you don't want more acronyms now, but we got to learn these. We've got an NS, an NA, an RS, and an RA. You need to know what each one of those messages does. So I don't just want to illustrate for you. It's right here on the board for you to study as well. But this is what happens, and the router advertisement messages are multicast. So good stuff to know there. Now something else that we're all going to have to get used to over the next few years, and we better be familiar with, is the IP version 4 to IP version 6 transition methods. Because it's not going to transit itself. We're going to have to be the transitors here. Because the theory is that as you roll out IP version 6, you start at the network edge and you work your way toward the core. And it makes sense. You don't want to try to do it all at one time. Very few of us are going to be able to do that just because of the size of the network. So we've got to come up with some ways for IP version 6 and IP version 4 to work together while we make the transition to an all IPv6 network. And to get this done, you're either translating or encapsulating. You're doing one of these two things. There are three primary methods of transition right now. And the first is the dual stack. And that's simply a node that supports both IP version 4 and IP version 6. What I'm seeing more of, though, is the 6 to 4 tunnel. And let me bring up a little illustration here. This is what 6 to 4 tunnels are like. Because Cisco documentation states that setting up one of these tunnels is very simple on the host ends of the tunnel. The interesting thing is that the tunnel, after it's configured, is actually dynamic. It's created when it's needed, it's torn down when the session ends, and it's much more scalable than any other solution. What happens is that a 6 to 4 tunnel is accomplished by taking an IP version 6 packet, and you see that's on the outside of our network here, and encapsulating it into an IP version 4 packet for transport across that section, the IPv4 section of the network, and then de-encapsulating it on the other side. So basically that tunnel means we're going to take an IPv6 packet, we're going to encapsulate it in an IP version 4 packet, transport it through the IP version 4 area, then when we get to the other side, we're going to de-encapsulate it for routing across an IP version 6 network. Now, 6 to 4 tunnels also have a reserved IP version 6 address prefix for the edge routers, such as the ones that we're looking at here. These prefixes begin with 2002, and they are followed by the router's IP version address expressed in hex. And just to show you what one of those looks like, again, it's the reserved address prefix for 6 to 4 tunnel edge routers. They begin with the number 2002. They are followed by the router's IP version 4 address expressed in hex, and they also carry a /48 prefix. And don't think that I just did a little typo there when I'm slamming together 6 to 4. That's actually the way you're going to see it in Cisco documentation. Takes a little getting used to. Our third transition method is network address translation protocol translation. NAT-PT. This is not regular good old network address translation that you and I have both come to know and love. This is totally different. Now, you need to know it exists. The configuration of it is difficult, and it is way out of the scope of the BSCI exam. If you know about it and you're considering it, you need to check Cisco's website for the latest requirements in the iOS versions to make it work, because not just any iOS version is going to run NAT-PT. And those requirements are going to change. That's why I'm not just going to put something on the whiteboard, because they could change a week from now. So really what I'm seeing for the most part are 6 to 4 tunnels. And for the exam as well, I think the emphasis is going to be there. I would know all three of these methods. I would know the basics just of what dual stack is and what that NAT-PT exists. But when it comes to 6 to 4 tunnels, I would know what the basic operation is. I would know that it looked a little something like that. You know, we're taking an IPv6 packet, put it in an IPv4 packet, send it across the IPv4 segment of the network, and then de-encapsulate it on the other side. And for both the exam and the real world, it's good to know what that prefix is as well, the reserved address prefix for 6-4 edge routers. And speaking of our old friend network address translation, we're going to revisit NAT. And again, if you've recently gotten your CCNA, you have a big leg up on your BSCI exam if you learned NAT. Not meaning to bash any of my competitors, including Cisco Press, but this is one of the problems with a lot of the books out there. They either ignore NAT or they kind of gloss over it, and mention, oh yeah, this is what NAT does, and then they don't really go into the detail of it. And a lot of people were failing the CCNA because of that. Make sure you have the NAT foundation down, and we're going to go over that right now. It's not complicated stuff, but like I said, a lot of books really gloss over it or just ignore it, and I know for a fact a lot of classes do too. Now, the reason we use NAT, and NAT is not going to disappear anytime soon, so we still need to know what's going on. The reason it works so well is because of what it allows us to do. It allows devices with private IP addresses to have those addresses translated into routable addresses for internet connectivity. And we've got 3 reserved classes, all RFC 1918 addresses. I'm sure you're familiar with that. You know the ranges. Just keep in mind for the exam in the real world that the masks that go along with them are not the classful masks. Sometimes out in the field I'll see, 8, 16, 24 here used for a mask. It's not the end of the world, but the masks are 8, 12, and 16 respectively. And there are 4 terms used to describe addresses at different points in the NAT process. And they can get a little bit confusing, so make sure you have these down cold before you go into the exam room. The first 2 you should know from your CCNA studies, inside local and inside global. The inside local address are used by hosts on the inside network, our local network. And they're going to be RFC 1918 addresses, because if they weren't, we wouldn't be using NAT. Inside global address, that's kind of a counterintuitive name, isn't it? Inside but global. Well, the inside global addresses are routable addresses used by the inside hosts. They are the translated addresses. Now, outside global refers to the addresses configured on the outside hosts, and that means the hosts on the other side of the connection. And these are fully routable addresses. Outside local are the actual addresses of the remote hosts that we're communicating with, and these are most likely, again, RFC 1918 addresses. Now let's take a look at a common NAT scenario, and you can see here on the left-hand side we've got a private workstation, 10111, that's a Class A private network. And what happens here is you can see that the packet goes out that Ethernet segment with a source address of 10118. And it hits the NAT router, and if the NAT router is configured correctly, it's going to translate that address into a routable address. And here it translated to 210.111. So it's routed normally, and it would hit the Cisco.com web server. And when it comes back, the destination address is 210.111. When the NAT router receives that, it's going to look at it, look in its NAT translation table, and say, okay, I mapped that to the inside address, 10.111. So then it will translate it back, and the workstation address will be able to get the packets back. NAT is totally transparent to both the workstation and the web server. In a way, it's a bit of a security feature because it does disguise what you're using as your inside private addresses. Unfortunately, in the real world, I could probably call 2 people at your company, pretend that I was a tech guy, and then just ask them to run a couple of commands, and I could get their addresses. So I don't look at NAT as a big-time security feature, but it is tremendously helpful in getting around the reachability issue for private addressing. So NAT works really well, and it's actually one of the drawbacks, I think, in getting people to learn IPv6. You know, the feeling seems to be, I'll do it when I have to because NAT works so well, I don't have to do it right now. Going back over the addresses that we talked about a moment ago, and we're looking at this from the host's point of view, from the workstation, the inside local address would be 10.1.1.1. The inside global address would be the address that is translated to, which is 210.1.1.1. The outside global address is a little tricky. It would be in this situation the IP address of the web server. And the web server is probably not going to use an RFC 1918 address, but if we were communicating with a workstation that was, and it was say 10.222, then that would be the outside local address. So the outside global address is what the remote device's IP address looks like to us from our workstation, but it could be different if they're running NAT, then the actual address of the device is outside local. Let's talk about the different kinds of NAT that we've got. And we've got static, dynamic, and what else have we got? We got PAT. Well, here's static NAT that I started and went in and configured in advance. And we're going with a scenario where the inside network that's going to have its addresses translated is 10.550. And they're going to be leaving out to the internet on the serial interface. And static NAT is just what it sounds like. You're going to create static NAT statements where you are mapping an inside address, an inside local address, to an inside global address. This is not the best usage of NAT, because the problem is you probably have multiple users in today's networks that have got to get out to the internet. We've got so many web-based applications that it's really not practical to say, okay, we're only letting 3 people out to the network. But in this case, that's what we've done. Only the hosts with the addresses ending in 5, 6, and 7 here would be able to get to the net. And when these routable addresses, the 210 addresses, were in use, they couldn't be used by anybody else. But when they're not being used, they couldn't be used by anybody else either. Because we can run the show IPNet translations command and see the mappings. But like I said, the problem is when those addresses are just sitting there, they're just sitting there not being used by anybody. And most companies don't have the routable addresses to just have them sitting there. So instead what we end up doing is configuring dynamic NAT. And what dynamic NAT allows us to do is create a pool of public IP addresses to be created. And the IP addresses will be mapped to private addresses as needed, and then that mapping will be dropped when the communication ends. So we're just going to write a mock one here on the router and use iOS help to go along, because the IPNet pool command is kind of long. The first thing you always do, and I know it's already there, but let's just say we were sitting down at this router and had not configured anything for dynamic NAT, always put your IPNet inside and IPNet outside commands on first. Not because the iOS demands it, but because that's the part people forget. I've done it. I've seen other people do it. You're so intent on getting the pool right that you forget to enable NAT on the interfaces to begin with. The inside interface is going to be the one closest to the inside network, and the outside interface is going to be the one facing the internet. So we've got this configured so far. Now we need to define who the users are that will be able to get addresses out of the pool. And you know what we do that with? An access list. We'll use access list 24. See, ACLs just come in all the time to your work. They really do. Since our access lists use wildcard masks, the ACL that I just wrote will enable users from the 10.550/24 network to get an address out of the NAT pool. Now I'm going to use the IP NAT inside source command to define the users that can use NAT. And I'm going to call the access list. That's the command that starts at IPNAT inside source. And let's see what my options are here. List, route map, and static. We just did static, which specified local to global mapping, but now we're going to use a list, and you see the definition there. Specify access list describing local addresses. Then, of course, we've got to put the list name or number. And there we go. List 24. And let's see what else we've got to do here. Specify interface for global address or name pool of global addresses. Well, this is dynamic NAT, so we're going to name a pool. We'll just call it NAT pool. And then that was it. We could use iOS help after that. We could use overload for the pool, but we're not going to do that. We're just going to define the regular pool, and that's it. Now we have to create the pool. And this can be the part on an exam for multiple choice that can be a little tricky. I'd be really familiar with the syntax of this command, IPNAT pool. First, we got to give it a pool name, and we already called it NAT pool in the IPNAT inside source command, so we better use that one. And we've got a couple of options here, but what we're going to do is put in the first IP address that will go in the pool, and we'll say it'll be 200.112. And now I have to specify the end address. Now again, this is a pool of addresses. When we enter this command, we're not saying just .2 and .5 will be in the pool and available for dynamic NAT. We're saying .2, .5, and everything in between. So we're going to have 4 addresses here, .2, .3, .4, and .5. And then finally, we do have to specify a network mask or a prefix length. I usually just go with net mask. And then we've got to assign the net mask that's going to be used for those addresses. That's one of the longer commands you're ever going to type. I mean, that's a long command. And knowing the syntax of that is a good idea. So we've done just about everything we need to do. We defined the ACL. We defined our inside and outside addresses. We used the IPNAT inside source command to define who could use this. And then finally, we created the pool itself. And show IPNAT statistics, again, will show us what we've got configured here. And at the very bottom there, since we've got dynamic and static running on the same router, you can see that total active translations is actually 3, but they're all the 3 static ones that we put on there. This is a great command for troubleshooting NAT. You don't really need to debug NAT. You need to do show IPNAT statistics. And you can see here at the end, dynamic mappings are all defined. The inside source is access list 24. The pool is NAT pool. There's the mask that we gave it. You can see that we missed a number when we entered it. I told you it was a good troubleshooting command. We've got a net mask of 255, 255, 25, 0. So we could take that NAT pool command off, and we'll do that before we leave. You can see the start and the ending pool of the addresses, and that we have a total addresses of 4. So you should be able to look at that and say, okay, you know, how many addresses do we have here? Well, you can run this command and it'll actually tell you. So let's take that NAT pool command off. Fortunately, if we use the up arrow to repeat the last couple of commands, we don't have to do all that typing again. And I'm going to take the previous NAT pool off. And remember, that's Control A to go to the front. I don't teach a lot of shortcuts with the keyboard because I like to let you develop your own. But that's a good one to do. Up arrow and then Control A. So dynamic NAT is going to work for us better than static NAT, obviously. We've got 4 addresses available in the NAT pool. First 4 come, first 4 serve, though. But what if we've got multiple hosts and 10 of them want to connect to the internet host to the internet simultaneously, and we only have 1 address to begin with? Well, that's where PAT comes in. That's port address translation. And it is generally referred to as overloading. And what's going to happen is that the private address and the port number are going to be translated to a public address and a port number. and that allows the same IP address to support multiple hosts. It is fantastic, and it works just beautifully. So let's take a quick look at what's going to happen with PAT, and then we'll actually look at a configuration of it. Give me just a moment here to call it up. Here we go. Now, 3 packets are coming to the PAT router from 3 different sources, and these packets need to all be routed out to the internet. And in this scenario, we don't have a pool of addresses just sitting around, and plenty of small to medium companies don't, because of course these addresses cost money. So what we're going to do here is configure port address translation, and you can see that the 3 inside addresses are all translated to the same outside IP address, or inside global if you will, but to a different port number. So the inside addresses are being translated to routable addresses. They're all being translated to the same routable IP address, but a different port number. So when the packets come back, the PAT router could say, okay, the destination is 210.111, port 1908. I map that to inside local address 10.111. I'll send it to that one. And this works beautifully. And the reason we call it overloading is because that's the keyword that actually helps us to make it work. And we're going to go over to router 2 here, so we don't have 3 different kinds of NAT running on the same router. And it's the same key command right here. We've still got to define our inside and outside interfaces. But now we're going to write the ACL right now, and we can do it in this mode. Access list 24 permit, and we're going to do the same network, which was 10.550.000.255. There's our ACL. Now we've got to enable PAT. Now we don't have anything to do with an address pool this time. We're not creating a pool. That's dynamic NAT. And it's the IPNAT inside source command again. And again, we've got our options here. We're going to use the access list number that we just wrote. But notice this time the choices we had were interface and pool. This time we're going to choose interface. Because the great thing about this is not only do we not have to have extra IP addresses to go into a pool, we're going to use the IP address of the serial 0 interface. We're going to use an IP address that we already have and that we're already using. And the word that makes it all work is overload. Overload and address translation. And that's it. Now you saw that you can overload addresses in a pool. You see that occasionally in production networks, but it's pretty rare. What you're really going to see is a single interface being overloaded. For the exam, it's a good idea to keep in mind that we could have used the overload keyword at the end of the pool command. When we put in IPNAT pool the first time, notice here that when we used iOS help, and this is why I'm always using iOS help, we could have overloaded the addresses in the NAT pool. We could do that. But what we did here was just use the one interface IP address we had, one that was already applied to serial 0, and we're actually going to overload that. So you can't beat that. You don't even have to have extra IP addresses to use NAT. Fantastic stuff. And finally, we'll revisit our old friend Cisco's 3-layer networking model. And of the networking models that you learned in the CCNA, you'll hear some reference to this one once in a while when people mention core switches. And just to remind you what it looked like, it is a 3-layer model. The core layer, as you would expect, is in the center. Distribution layer in the middle, and access on the outside. The access layer is where host devices and end users actually interact with the network. But generally, your layer 3 devices are also found in the access layer as well. This is kind of the outside of the network. That's where your routers actually are. The distribution layer, this is the workhorse. Because the key purpose of the distribution layer, basically is to do all the dirty work that we don't want the core to handle. And looking at the previous board, just a few of the distribution layer's tasks are listed there. Traffic filtering, internet access, policy routing, address aggregation and summarization, inter-VLAN routing, and route redistribution. You know, that's all. And a couple of other things. Good idea to know what's going on there at the distribution layer. And why then do we want to keep the load off the core layer if it's the core layer? You know, why do we want the distribution layer doing all the dirty work? It's because of the core layer, we're interested in only really one thing happening: rapid packet switching. You've heard the term core switches. This is what we're talking about, because switches are found at the core layer in Cisco's 3-layer networking model. And everything we do on a Cisco device has a cost in router resources. And any traffic filtering that we do, or any of the other things that the distribution layer handles, that's going to have a cost on our core devices. We want two things at the core layer: rapid packet switching and redundancy. We'll take all the redundancy in our switching network that we can get. So since the core layer is indeed the core of the network, any connectivity issues we have do impact the entire network. So the more redundancy we have, the better off we are. And the more work that the distribution layer keeps off the core layer, that allows the core layer to focus on what it needs to do, which is switching. We want to keep those core devices pure, and we want to do all the filtering we can and all the other services that we can at another layer, which is most likely going to be the distribution layer. And you know there's got to be an exception, right? There's got to be an exception here somewhere. Can't be that clear-cut. QoS, quality of service. You'll start to get a taste of quality of service when you take your CCNP switching exam. But basically, quality of service allows us to tag data as to its importance, put it in a high importance queue, put it in a low importance queue. That's just basic QoS. It gets a lot more complex than that. It gets a lot more granular. You can really tie your network down as to what traffic gets handled first with quality of service. And one feature of that, as I just mentioned, is the ability to mark or tag certain packets as having the highest priority at times of network congestion. Well, if we look at that 3-layer model again, the device that's going to be the best judge of the congestion is the core layer. So quality of service is the one feature that is often configured at the core layer rather than the distribution layer. But again, looking at that list of tasks, the distribution layer is handling a lot of other stuff. But when we configure quality of service, we're basically doing it at the core. And that's really it for the 3-layer model. And as I mentioned at the beginning of this lecture, I want to give you a final word on IPv6, or really two final words. Learn it. Because again, I will admit to you that when I first looked at IPv6, I thought, what do we need that for? You know, what's wrong with IPv4? And we've talked a little bit about why it's here, and of course, technology is growing every single day. And we are in a field where you have to keep learning. You've heard that from other people, but I just want to reiterate to you, you've got to keep learning to keep your edge in this field. And what you must not do is take the approach of, you know, well, we use IP4 at my job, so I don't need to know IP version 6. Okay, I heard the exact same thing when Microsoft moved to Windows 2000 Server. And you had all these people who used Windows NT 4.0, and a lot of them frankly screamed bloody murder and just said, oh, you know, we're an NT4 shop and we're going to use that forever, and I don't need to know Windows 2000 Server. You cannot take that approach to your career. Because I'll tell you point blank, I know some people that approach didn't work out too well. If you only know NT 4.0 right now, you're not in good shape as far as your career goes. So my point is not to bash the people who are saying that. It's that you can't afford to take that approach. When things change, and they are always going to change in our field, we've got to learn it. few of us are ever going to work in one place in IT for the rest of our lives, just the way the field is. And to get ahead and to remain marketable, we have to know the current technologies, and we have to know things that maybe other people don't want to take the time to learn. And IP version 6 is one of those things. Because people who know IP version 6 over the next couple of years, you are going to have a tremendous advantage over people that do not. And again, I've only given you an introduction to IP version 6 here. There are plenty of good free resources out on the web that will give you a good start. Then you might want to look for some books. And there's a lot of solid information available readily through your favorite search engine. Some of it is Cisco based, some of it is not, but that's fine. Take the incentive now and learn IP version 6, because I promise you, you will be glad you did.